This is the wave simulation. So the purpose of this activity is to observe how the different properties of a wave affect each other. So there are some references. There's, of course, the simulation that's on the right side of the screen. I will provide this video, and there is a video that will help you tell the different parts of the wave. So there's no equations for this one. Any equations or anything that's be calculated will just be told in the directions. So the first thing that you're going to do when you open it up, you can see that there's a picture. There are pictures and directions that tell you exactly how to set this up. So for all of these, what you want is you want to come over here and click the oscillate button, right? We want it to oscillate, and we don't want an end. We want that wave to go out the window. We just want it to keep going. Then the first part, what we're doing is we are changing the frequency, and we are measuring and calculating everything else. So let's just set the amplitude. The amplitude says 0.6 centimeters. The frequency is going to start at 2 hertz. So it'd be easier to just drag this little toggle up to 2 hertz. Damping, we don't want any damping. We want that wave to just be continuous. And the tension, we want it on high. And I want to click everything that I have access to. So first thing is we are going to calculate the period. So we don't need to do anything with the simulation. We just need to calculate it using the hertz. And it tells you exactly how to do this above each column. So I'm going to go ahead and get my calculator out. And to calculate the period, it says 1 divided by the frequency. So basically the inverse. So 1 divided by the frequency is 2. You're going to get 0.5 seconds, right? 0.5 seconds. So remember, so that's how you calculate the period. Now the wavelength we're going to need to use the simulation. Now I can slow this down. That might help things out, but I'm also going to pause it. So remember, the wavelength is from the point to point. So it says use the ruler. What we need to do is we need to take that 0, and I'm going to place it on the crest. So I'm going to just place it right on top of the crest, and I'm measuring crest to crest. So that would be, that's about, let's see, it's not quite, each one of these dash marks is 0.2 centimeters. It's not quite on 3, and it's not quite on 3.2. I'm going to say this is 3.1 centimeters. You can see here it turns green, and the graph is already going to start to develop for me. Now I need to, this one's kind of the trickier one. We need to use the time and the ruler to calculate the time it takes for this wave to traverse 5 centimeters. So what I'm going to do is I'm going to put this reference line right here on the crest. That way I can tell when it goes. Now what I'm going to do is I'm going to place this 0 right above the green ball by the little oscillator. So 5 centimeters, you can see, is over here. That is right where this green ball is. So essentially what I'm doing is I'm counting how long it's going to take that energy to travel that 5 centimeters from that green ball on the 0 centimeter mark to the green ball on the 5 centimeter mark. So I set this on slow motion because it's pretty hard if it's going normal. And slow motion will give me a little more accurate reading. So I'm just going to take my stopwatch, and as soon as that green ball hits that 0, I'm just going to start the stopwatch. And then when this green ball over here hits that 5, I'm just going to stop the stopwatch. So ready, go. So about 0.79 seconds. I'm just going to come in here, 0.79 seconds. Perfect. Now I can calculate the speed that this wave is transferring that energy from place to place. So 5 centimeters, well, the wave speed is basically taking 5 centimeters. So I'm going to come in here, bring my calculator up, hit clear. There we go. And I'm going to take 5 centimeters divided by the time it took that wave to transfer that energy, those 5 centimeters. So I'm going to take that divided by 0.79, and I get 6.32. I might 6.33, right? That's probably accurate. So 6.33. All right, perfect, right? So I know it turns green. My graph is going to start to be accurate. Then the next thing that you're going to do, notice like we keep everything the same, except now we're going to just increase that frequency to 2.5, right? And I'm just going to do that all the way down to 3 hertz. So Now the next one, let's go down to the next section. So I want to keep this, I'm going to keep it on oscillate. I want to keep it on no end. I'm just going to restart my watch. So on this one, what we're doing is we're changing the tension of the string. So the amplitude, let's see, is set at 60. The frequency is going to be at 1 hertz. Wait, all the way up here to 1 hertz. There we go, right? Damping. Now, this starts with the string tension down low. So I'm going to go ahead and just hit normal just to let these waves continue out. So in this one, I need to measure the wavelength. So I'm going to do the same thing I did in that first one. I'm going to pause it. Now I'm going to go from crest to crest. So I'm going to find a crest. I'll just do one in the center. I'll just go from here to here. So you can see here it's at about 1. This is 1.2. It's not quite on 1.2. It's a little bit above that. It's not quite halfway in between, which would be 1.3. I'm going to say this is about 1.25, right? 1.25. There is some wiggle room in there, but you can see here that it's already going to start to generate my graph. So now what I'm going to do is I'm going to do the same thing, the time it takes to travel 5 centimeters. Sorry. So I'm going to come in here and I'm going to do that same thing. Just place it there. I'm going to put it in slow motion though. Right. So I'm going to take this stopwatch out and let's see here. So once again, like you can see here, this green dot over here is still on the 5 centimeter. So I'm going to time once the green ball on the oscillator hits the 0, I'm going to start the stopwatch. And then once that energy, once that wave gets to this green ball hits the 5, I'm going to stop the stopwatch. So on your mark, get set, go. You can see that this one is taking a little bit longer. It's just crossing the 2. Go at the 3, the 4. All right, and that green ball is going to stop it. There we go. So look at that, 4 seconds. So I'm just going to put 4 seconds. Now I need to calculate the wave speed again. So I'm going to come into my calculator, and then I'm going to take 5 centimeters, right, divided by the time it took to travel 5 centimeters, which is 4 seconds, 1.25. 1.25. Perfect, right? 1.25 centimeters per second. You can see here the graph is already starting to form with that one. All right, so in this one, what you're doing is you're changing the tension. So I'll let this go normal. Now the next one is the medium. So you can see here my tension. I just want to line that toggle up right on the medium, right? So now we're in the medium tension. The last one gets tricky when it's at the higher tension. So measuring the wavelength can be kind of tricky here. I just put this one on slow motion, and like once it gets to the peak, what I do is I just, not the stopwatch, I pause it, right? Once it gets up there, because you can see here, like it's almost all the way out the window. So usually what I do is maybe once that green ball is just at the peak, right, when it hits that red line, I just pause it. So now I can measure that green ball. That's the peak to the next peak. So you can see here it's over 6 centimeters. So that's probably one of the trickier measurements to make in this simulation. So now the next one, we come down here. All right, now we're changing the amplitude of the wave. So let's go ahead and do that first one, right? So the first amplitude, I'll let this play. There we go. All right, I'm going to set this one down. The amplitude starts at 0.2 centimeters. The frequency is at 2 hertz, right? So we're keeping the frequency the same throughout this one. So there we go. All right, it's 2.01. Now it's at 2. Perfect. All right. So we still want damping none, and the tension's going to be at high for this whole thing. So now what I'm going to do is I'm going to measure the wavelength, and now I'm going to move my little reference laser down here just so I can tell where it is, and I'm going to just pause it. Now I'm going to go peak to peak on this one. So I'm just going to move the peak there, so put the 0 there, and then I'm going to go to the next peak. You can see here it's past 3, not quite at 3.2, probably at 3.1. I'm just going to put 3.1 there. All right. Now what I'm going to do is I'm going to do the same thing. I'm going to time how long it takes to go 5 centimeters. So I'm just going to place that 0 on that line. And once that green ball hits, I am going to time it out, time how long it takes to get to this 5 seconds when this green ball over at the 5 seconds hits the ruler. So go. Boom, there we go. So 0.8. All right, so I come over here, 0.8 seconds, and now I can calculate the wave speed again. So I come in here, I get my calculator out, and it's going to be 5 centimeters divided by the time that it took to go 5 centimeters. So 0.8. Perfect. 6.25 centimeters per second. And you can see it turned green, and I am creating a nice little graph here. So the questions down here, just basically the first ones are asking you to identify the different different parts of the different properties of the wave, like give us the definition. The next one is looking at the graph, saying, okay, well, what happens when the wavelength, what happens to the wavelength if the frequency increases? Use the data in the graphs to answer how the frequency, wavelength, the wave speed, and the period affect each other. The next one asks about the amplitude, how the amplitude affects the other ones. You can see here the last questions are like free response ones. What's the difference between a wave's frequency and period? How do they affect each other? Use the data in the graphs to answer this question. What affects the wave speed? What happened to this? What did we do in this simulation to affect how fast that wave went? So once you get all of the graphs, you should be able to answer those questions. So once again, this is the wave simulation.